Hi, this is Alex from devstories.eu, Python, Cheminformatics, and AI, episode 13 of 22. In chemistry, a single atom out of place can turn a potent, life-saving drug into an inert powder. These sudden drops in biological potency are called activity cliffs, and they are the absolute nemesis of traditional AI models. An activity cliff occurs when you have a pair of molecules with high structural similarity but significantly different activity levels. Consider a concrete scenario. You have two molecules that share 90% of their structural framework. The first molecule binds tightly to a biological target. The second molecule is completely inactive. The only physical difference between them is a single methyl group attached to a specific ring. To a human medicinal chemist, this specific structural modification is highly informative. It tells them exactly where the boundaries of the receptor pocket are. To a standard machine learning model, it is a catastrophic disruption. Here is the key insight. Most deep learning approaches in cheminformatics are built to predict absolute property values. Whether you're using a graph neural network or a chemical language model, the architecture is fundamentally designed to map chemical structures into a continuous mathematical space. The core assumption hard-coded into these models is that similar molecular structures should map to similar biological properties. When a standard model processes our two nearly identical molecules, it generates representations that are right next to each other in that mathematical space. Because the inputs are close together, the model naturally outputs nearly identical absolute potency predictions for both. Activity cliffs fundamentally violate this assumption of a smooth, continuous chemical space. They represent a severe discontinuity. The model expects a gentle hill but encounters a vertical drop. This problem is heavily amplified by the nature of drug discovery data. Experimental datasets are notoriously limited and noisy. When you train a deep neural network on sparse data, the model struggles to generalize. To minimize overall error across the training set, the network learns broad, global patterns. It smooths out the local irregularities. When it encounters an activity cliff, the standard regression objective treats that sudden jump in variance as experimental noise or an outlier. The model ignores the most critical piece of local structural information because it does not fit the global trend. This is why predicting activity cliffs remains one of the hardest problems in molecular property prediction. The models are forced to learn a discontinuous chemical space directly from limited data. Because they focus entirely on absolute predictions for single molecules, they completely ignore the valuable information hidden in the relative differences between matched molecular pairs. In many cases, simpler tree-based models actually end up outperforming complex neural networks on these datasets simply because deep learning models oversmooth the representations. The assumption that similar chemical structures always yield similar biological activities is a useful statistical baseline, but it is not a physical law. Activity cliffs are the brutal, discontinuous reality of structure-activity relationships, and they prove that predicting absolute properties in a vacuum will always fail at the margins. Thanks for spending a few minutes with me. Until next time, take it easy.